Hey everybody, welcome back to Dave's Math Channel. This is my continuing feature on my daily math problems, which I've been posting on the Facebook group Classical Mathematics. I don't usually do this, but I actually did two in a row. I featured a daily math problem yesterday. I usually do these every few days. But anyway, the one I did yesterday was pretty complicated, involved Foucault pendulums. Today is going to be a much simpler one. Today I'm going to talk about pi approximations of pi. So anyway, let's get started. So here's the problem. The problem is to find all pairs m comma n of positive integers with m up to 100,000 such that the absolute value of n minus pi m is less than 0.0001. In other words, 1 part in 10,000. So these are basically just good rational approximations of pi. Um, so anyway, how do we do this? Well, I did this by brute force. It's easy enough if you have a good mathematical software, which I do. I have Mathematica on my computer. It's straightforward enough to write code to do this problem, which is what I did here. There's also a way you can solve problems like this using continued fractions, but that's a lot more complicated. I didn't do it that way. So here's my code, and in case you can't read this, what this is doing, it goes through a for loop here. I'm letting m go from 1 to 100. Remember, m was the positive 100,000. So I'm letting m be the smaller of the two integers in this case. And n is supposed to be approximately pi times m. So for every value of m, I'm multiplying it by pi and seeing how close that is to an integer. So if it's within 1 part in 10,000 of an integer, which I'm calling n if it is, then I save that value of m and n. Otherwise, I don't. And I keep going through this for loop until I let m get all the way to 100,000. And since computers are very fast at solving problems like this, that took my the mathematical almost no time to solve, and here are the results. So they're actually. It turns out there's exactly 23 pairs m comma n, and I list them all here in this table. I kind of doctored this table for this slide, and Mathematica writes them all in one set. But I have 12. I have 12 pairs on the left and another 11 pairs on the right. M is in the first column, N is in the second column, and the third column is the absolute is m minus pi times n. For some values of m and n, it's negative. For others, it's positive, but the absolute value is always less than 1 part in 10,000. Yeah, one thing I find interesting about this output, and this is true for every irrational number alpha, it turns out. I don't know how to prove this, but it always turns out that there's exactly two steps of intervals, two different sizes of steps of intervals. And the smaller of these steps in this case is 113, comma 355. And another thing to note here is that 355 over 113 is a rational convergent of pi. I think I have another slide where I show this. Yeah, I should have gone to this slide here because I explain this in a little more detail. But yeah, so there's two different types of sizes of intervals here. The first is the order pair 113 kind of 355. You can think of that as a vector if you like. And then there's a bigger vector, 32,537. That's the big interval of m. And the bigger interval of n is 102,218. So we have exactly two intervals between these pairs of solutions. And I believe it's always the case, no matter what alpha you start with, as long as alpha is irrational. I think it might even work if it's rational. If it's rational, you can get just one interval because you get exact values. Not even an epsilon. Epsilon could be 0 if it's rational. But if you start with arbitrary values of what I'm calling alpha, let me just go back to this slide here. The code I wrote, I didn't explain this very well, but the code I wrote doesn't just work for pi. It doesn't just work for the values I give in the problem, namely alpha equals pi. That's the number we're trying to approximate. And it doesn't just work when your upper bound on the error is 0.0001. We can make that an arbitrary positive number epsilon, and we could also make the limit on m an arbitrary positive number, which we could call m max. So that's how I wrote my code. It'll work with these three arbitrary parameters, and it should work for all of them. And as long as alpha is irrational, I believe it's always the case that you just get two sizes of intervals, and you keep getting them ad infinitum. And you also get a really interesting structure. I don't talk about this in the solution, but if you graph these solutions, you get what's called a quasi-lattice, so one-dimensional quasi-lattice. This is a pretty new area of math, quasi-lattices and quasi-crystals, but you can even define quasi-lattices this way. In one dimension, it's kind of trivial, but basically what you're doing is you're projecting approximations of an irrational number onto a line. That gives you a one-dimensional quasi-lattice, which this is. Anyway, I just thought I'd point that out. And another thing I think I should point out before I finish here is that these two intervals give you very good rational approximations of pi. The first one, 355 over 113, that only differs from pi by, I think it's 8.5 times 10 to the minus 8, which is less than 1 part in 10 million. And the other interval you get if you translate into a rational number, 102,218 over 32,537. That's not a rational conversion, it turns out, but it's still a very excellent approximation of pi. As a matter of fact, it's even better than the other one. This one just differs by about 1.7 times 10 to the minus 9, less than 2 parts in a billion. So all these estimates are very close to pi. And anyway, like I said, you can solve problems like this. In general, you can solve them analytically using continued fractions. I haven't actually worked out the method for doing that, but there is a method for doing it using continued fractions, although this one was straightforward enough to do with a brute force computer search, which is the way I did it. So anyway, that completes my solution to this daily math problem. So thank you for watching. Long live math, and I'll see you guys next time. Bye.